Picture the surface of Mercury, but not the Mercury of popular imagination, not the sun-blasted hemisphere, the face forever scalded by radiation. This is the other side, the night side. The sun set weeks ago, and it will not rise for weeks more. Above, the stars hold steady in a sky that offers nothing between them and the eye. No atmosphere to scatter their light, no haze to soften their edges. They are simply there, absolute and unwavering, against the black that has no gradient. Beneath insulated boots, the regolith radiates the memory of heat outward into vacuum, silently, continuously. It is, by any measure, a desolate landscape, and yet something is happening here that science took centuries to notice. Point the detector, one tuned to a precise and narrow wavelength toward the anti-solar point in the sky, the direction directly opposite where the sun waits, below the horizon, patient and enormous. Look carefully. Something faint stretches away from the planet into the dark, an elongated glow, barely there, extending for millions of kilometers into the blackness. A ghostly structure trailing behind this small, battered world like smoke from an ancient and invisible fire. Mercury, the smallest planet, the closest to the sun, the one geology textbooks once dismissed as inert, is venting something into space. Not gas, not ice, not dust in the sense that comets lead dust. Sodium atoms. For most of observational history, Mercury offered little to hold the imagination. Ancient astronomers tracked it dutifully across the sky. Mariner 10 photographed its cratered face in 1974. Messenger orbited it for 4 years, beginning in 2011. By the early 21st century, Mercury was understood as the runt of the inner solar system. Small, hot, geologically quieted, its story mostly written. But sodium had been detected in Mercury's exosphere since the mid-1980s, and by the 1990s, planetary scientists were using specialized sodium filters to observe the planet more precisely. In 2001, a team working at McDonald Observatory in Texas was conducting one such survey when the data returned something unexpected. A faint emission extending far beyond the visible disk of the planet itself. Not a slight blurring at the edges, a structure, long, directional, enormous. The initial interpretation was instrument error. The team checked and rechecked. They examined their calibrations. They looked for artifacts in the data processing pipeline. The structure remained. What McDonald Observatory had captured was a sodium tail stretching approximately 2.5 million kilometers behind Mercury. To situate that number physically, it is roughly 700 times the diameter of Mercury itself. Had it been visible to the naked eye, it would have appeared as one of the longest features in the inner solar system, comparable in relative scale to the most dramatic cometary tails observable from Earth. The finding was not merely surprising. It was, in the specific language of planetary science, paradigm adjusting. The classification of which solar system bodies can sustain a tail had, until that moment, rested comfortably on a single category: comets. Small, icy, volatile, rich bodies whose near-solar passages vaporize their surfaces and leave behind streaming clouds of gas and dust. Planets, rocky, massive, geologically settled, were understood to possess no such mechanism. Mercury, it turned out, had not received that memo. Understanding how Mercury produces its sodium tail requires setting aside the familiar model of cometary behavior and building a different picture from physical first principles. A comet generates its tail through sublimation. Ice converts directly to gas under solar heating, releasing molecules that are then pushed anti-sunward by radiation pressure and the solar wind. The process is essentially thermal, driven by the delivery of heat to a volatile substrate. Mercury has no such substrate. The ice deposits that may exist in its permanently shadowed polar craters remain stable precisely because they are never exposed to direct solar radiation. The rest of the planet is rock, silicate minerals, trace metals, and sodium. What creates Mercury's tail is not heat alone. It is the sum of two distinct physical processes, each operating continuously and simultaneously. The first is sputtering, At perihelion, Mercury's closest approach to the Sun, at roughly 47 million kilometers, the planet intercepts solar radiation at intensities approximately 10 times greater than Earth experiences. Accompanying that radiation is the solar wind, a continuous flux of charged particles, predominantly protons and electrons, traveling at velocities approaching 500 kilometers per second. When those particles strike Mercury's surface, they do not merely deposit energy, they transfer momentum to individual atoms in the uppermost layer of the regolith. Picture a cascade. An incoming solar wind ion strikes a surface atom, which recoils and strikes its neighbors, propagating energy through the lattice until a weakly bound surface atom receives enough momentum to escape entirely. This is sputtering, a collision cascade that effectively chips the planet's surface atom by atom. The key variable is binding energy. Not all surface atoms are equally difficult to dislodge. Sodium, as it happens, is among the most weakly bound elements present on Mercury's surface. Data from MESSENGER confirm this in quantitative terms. During periods of elevated solar wind activity, sodium group ion concentrations in Mercury's exosphere increase by approximately 50%. The planet responds to the solar wind's intensity almost immediately, releasing sodium in proportion to the bombardment it receives. The second process is micrometeoroid impact vaporization. Mercury possesses no atmosphere. There is nothing to slow incoming debris, no layer of air to ablate small particles before they reach the surface. Even dust grain-sized meteoroids, traveling at tens of kilometers per second, strike the regolith with enough energy to vaporize both themselves and the volume of surface material far larger than their own mass. The result is a localized burst of liberated atoms, including sodium, injected directly into Mercury's exosphere. Some researchers have identified periodic enhancements in the sodium tail's brightness that correlate with Mercury's passage through denser streams of interplanetary dust, debris shed by comets along their orbital paths. When Mercury moves through such a stream, micrometeoroid bombardment intensifies, temporarily increasing the rate of surface vaporization and feeding more sodium into the exosphere, and subsequently into the tail. The tail itself, then, is a kind of record, an ongoing log of what Mercury is passing through. Neither sputtering nor impact vaporization explains the tail's form. They explain the source, the mechanism by which sodium atoms leave Mercury's surface and enter its exosphere. But the structure that extends 2.5 million kilometers behind the planet, directional and coherent, is shaped by something else entirely. It is shaped by light itself. Photons carry momentum. This is not intuitive, they have no mass, and everyday experience offers no analogy, but it is one of the foundational results of 20th century physics. When a photon is absorbed by an atom, a tiny quantity of momentum is transferred in the direction the photon was traveling. The atom then re-emits a photon in a random direction, which carries away an equally tiny quantity of momentum in that random direction. The net effect, averaged across many absorption-emission cycles, is a small but consistent push in the original direction of the incoming photon. For sodium atoms in Mercury's exosphere, the incoming photons arrive from the Sun. The push, therefore, is consistently anti-sunward. This is radiation pressure, and for sodium, it is remarkably efficient. Sodium absorbs solar photons at a specific wavelength, 589 nanometers, in the yellow portion of the visible spectrum, with high probability. Each absorbed photon delivers its small momentum kick. The process repeats thousands of times per second. The cumulative effect is a persistent, directed force that gradually accelerates sodium atoms away from Mercury against the planet's weak gravitational pull and out into interplanetary space in the direction opposite the Sun. The result is a structure that consistently points anti-sunward, not because the solar wind is blowing it back, as happens with cometary ion tails, but because sunlight itself is pushing the atoms outward. Mercury's sodium tail is, in this sense, a structure created by photon pressure alone. The same physics that creates the tail also makes it detectable. Sodium is what spectroscopists call a resonant scatterer. When a sodium atom absorbs a photon at 589 nanometers, the outermost electron briefly jumps to a higher energy level. When it falls back, it releases a photon at the same wavelength. The atom is, in effect, re-emitting solar light at a very specific color, the deep yellow of sodium vapor, the same color as low-pressure sodium street lamps. This emission is happening continuously throughout Mercury's exosphere and along the entire length of its tail. But the signal is faint, extraordinarily faint against the broader glare of the solar system. Standard optical telescopes, which collect light across a broad range of wavelengths, simply cannot isolate it. The tool that makes the tail visible is a sodium D-line filter, a narrow-band optical filter that transmits only light at and around 589 nanometers, blocking everything else. With such a filter in place, the broader solar glare is removed, and the sodium emission, faint but real, stands distinct against the dark background of space. This is what the McDonald Observatory team was using in 2001. The tail was there all along. It simply required the right instrument and the right orientation to see. Mercury's sodium tail is not a static feature. It breathes with the planet's orbit, varying dramatically in length, brightness, and structure across the 88-day orbital period. Mercury's orbit is among the most eccentric of any planet in the solar system. Its distance from the Sun varies from approximately 47 million kilometers at perihelion to 70 million kilometers at aphelion, a difference of nearly 50%. This variation has profound consequences for the tail's behavior. At perihelion, solar radiation and solar wind intensity are at their peak. The rate of sodium ejection from the surface rises sharply. One might expect then that the tail would reach its maximum brightness at perihelion itself. It does not. Observations reveal that peak tail brightness occurs approximately 16 days after perihelion, a delay that puzzled researchers until the orbital mechanics were examined more carefully. The explanation involves a phenomenon called the Fraunhofer absorption lines, and specifically the sodium D lines within them. The Sun's own atmosphere contains sodium, which absorbs outgoing solar photons at 589 nanometers before they can travel outward. In the solar spectrum, as seen from a stationary observer, the sodium D lines appear dark, absorbed. This means that the photons most available to drive radiation pressure on Mercury's sodium tail are precisely the ones that the Sun is removing from its own output. The driving force is diminished. But Mercury is not stationary, it is moving, and as it moves, particularly as it accelerates past perihelion and begins moving rapidly away from the Sun, the Doppler effect shifts the wavelengths of the incoming solar light as seen by the sodium atoms in the exosphere. The absorption spectrum shifts. The dark sodium lines in the Sun's spectrum are no longer aligned with 589 nanometers as experienced by Mercury's atoms. Different photons, not absorbed by the Sun, become available for the tail to scatter. The faster Mercury moves away from the Sun, the greater this Doppler shift and the more efficiently the tail can absorb and re-emit solar photons. At maximum recession velocity, which occurs not at perihelion itself, but roughly 16 days afterward, the tail reaches peak efficiency and maximum apparent brightness. This is, in the fullest sense, an atomic phenomenon operating on a planetary scale. The behavior of a single line in the solar spectrum interacting with a Doppler shift driven by orbital mechanics determines when a 2.5 million kilometer structure becomes most visible to observers on Earth. Understanding when the tail is brightest does not resolve the practical challenge of seeing it. Multiple conditions must align simultaneously. First, Mercury must be at sufficient angular separation from the Sun in Earth's sky, what astronomers call elongation, to be observable at all. At minimum solar elongation, Mercury is too close to the Sun's glare for ground-based observation. Second, Mercury must not be positioned behind the Sun from Earth's perspective. Superior conjunction renders the planet completely unobservable. Third, the geometry of the tail must be favorable. Earth must be positioned such that the anti-sunward direction of the tail is pointing away from us at an angle that allows its length to be observed, rather than foreshortened. The convergence of these three conditions is rare. Optimal observing windows for Mercury's sodium tail occur only during specific periods, spaced years apart. That the McDonald Observatory team captured the first confirmed detection as early as 2001 was, by any honest assessment, a remarkable alignment of preparation and fortune. Subsequent observations have used coronagraphs, instruments that block the sun's direct disk, extending the range of conditions under which faint solar-adjacent phenomena can be detected. Through these tools, the tail has been imaged repeatedly, and its variability documented in quantitative detail. Each observation confirms a structure that changes with orbital phase, brightening and dimming, extending and contracting in precise accordance with the physics that produces it. Mercury's sodium tail, considered in isolation, is already an unexpected feature of a body long assumed to be geologically and atmospherically inert. Considered in broader context, it opens several lines of inquiry that extend well beyond Mercury itself. On planetary evolution, the processes generating Mercury's tail, sputtering, and micrometeoroid impact vaporization represent a slow, continuous erosion of the planet's surface. Sodium is being depleted from the uppermost regolith layer on timescales that, while negligible by any human measure, become significant across billions of years. Mercury's surface composition today is, in part, a product of this ongoing loss. The same logic applies in reverse. The tail is a record of what Mercury's surface once contained. This opens a window onto questions of surface chemistry evolution, how the composition of airless bodies changes over geological time, as volatiles and weakly bound elements are preferentially stripped away by solar bombardment. On exoplanetary science, the implications extend beyond this solar system. Many exoplanetary systems contain what are called hot Jupiters, gas giant planets orbiting at distances far closer to their host stars than Mercury orbits the Sun. If Mercury, a small rocky planet, can sustain a sodium tail extending 2.5 million kilometers, the atmospheric loss from these close orbiting giants is likely to be orders of magnitude larger. The spectroscopic techniques developed to identify and characterize Mercury's tail, particularly the detection of sodium D-line emission, are now being adapted for the study of exoplanetary atmospheres. By searching for characteristic sodium emission signatures in the light curves of transiting exoplanets, astronomers may be able to detect analogous tail structures around distant worlds and infer details about their atmospheric composition, stellar environment, and mass loss rates. Similar sodium emission features have already been detected around Earth's own moon, suggesting that the process is not unique to Mercury, but common to any sufficiently exposed airless body operating in the inner region of a stellar system. At the broadest level, Mercury's sodium tail is evidence that the boundary between a star and its nearest planetary neighbor is not a passive one. The Sun is actively reshaping Mercury, removing material from its surface, accelerating that material into space, and sculpting the resulting structure through radiation pressure. The planet is not merely orbiting, it is being eroded. This dynamic, star acting on planet, continuously at the atomic level, is the dominant process governing the long-term evolution of any planet that lacks sufficient mass, magnetic shielding, or atmospheric depth to protect its surface. Understanding it in the specific, measurable terms that Mercury provides is the foundation for understanding analogous processes wherever stars and planets exist in close proximity. The Bepi-Colombo mission, a joint ESA-JAXA spacecraft that has completed multiple Mercury flybys and is scheduled to enter orbit in 2025, will bring unprecedented instrumentation to bear on these questions. Its suite of particle detectors, magnetometers, and spectrographers will observe Mercury's exosphere and tail at resolutions and sensitivities that ground-based observation cannot approach. The data it returns will almost certainly revise the current model in ways that cannot yet be predicted. What is already clear is this: a planet that appeared, for most of observational history, to be among the solar system's most straightforward objects has proven to conceal complexity at every scale. A tail visible only to specialized instruments, a brightness peak governed by atomic physics and orbital mechanics simultaneously, a record of surface loss written in the spectrum of escaping sodium. Mercury is doing something in the dark that took the 21st century to see. The question of what else it might be doing, what other processes are operating, quietly, just below the threshold of current detection, remains open. The universe, it turns out, rewards patience and precision in roughly equal measure, and the smallest planet in the solar system has not yet finished offering surprises.